So there's, well, 3 trig ones, where if you try to find the limit as x approaches 0, you would get 0 over 0. So that's the indeterminate case. So this is a rule that you're just going to have to memorize. And there's really, if you look at the graph of this function, which has actually come up before, I don't know if you remember it, but it did come up before. I didn't really call much attention to it because I wasn't really ready for you to know it and memorize it. But if I show you the sine of x over x graph, it'll be pretty easy to tell what the limit is as x approaches 0. I'm just going to go negative 5 to 5 on all of these. Right, 1. Okay, so the answer to this is just 1, and it's just a rule you have to know, and we will use quite often. So. Yeah, that we kind of explored that. Just was that 2 nights ago's homework? Had you exploring that? Sine of 2x over x will be 2. Yes, it will. Yep. Yep. So we will, I actually, moving forward, I don't get that answer by memorizing it. I'll show you a different alternative method that'll be more encompassing and will work for more variations of this. But sine of anything divided by that same thing will always give you 1. That makes me totally think horizontal asymptote, so I can't really get past that. This does have to match this verbatim. So sine of 15z over 15z would equal 1 when you're taking the limit as it approaches 0. Josh, what's your question? Okay. I mean, if that's helpful for you, the limit as z approaches 0 of the sine of 15z over 15z would also equal 1. So whatever you're taking the sine of, if it's over that as well and you're asking for the limit, it's going to be 1. And then this second trig function, again, if you plug in 0, up top you're going to get 1 minus 1. So 0 over 0, it's the indeterminate case. So if we look at the graph of this one, 1 minus cosine x is our numerator, all over x. The limit as you approach 0 is 0. And the order of subtraction doesn't really matter. Essentially what we're doing from this function to this function is negating it. If you negate a function, what are you doing to it? Flipping it vertically. So your limit is still going to be 0 even if the order of subtraction is flip-flopped. Josh? Not 1 minus cosine squared. If they wanted you to find 1 minus cosine of x squared over x squared, that would be okay. As long as this and this are the same. Okay? I can't remember which one it is, but I think it's this one. What did I do to the function when I just typed it in? I flipped it, okay? And I think, oh no, this one wouldn't be, right? When you flip 0, you get undefined. So it makes sense that when I flip it, there is an asymptote. What about the sine x over x? What if I make it x over the sine of x? What happens when you reciprocate 1? Still 1. So this one, because the limit was 1, this one works if you flip it to the reciprocal as well. So if you want to write like a 1b, the limit as x approaches 0 on x over sine of x is also 1. So we can use that. So the sine x one works in either order as far as reciprocals are concerned. Sine x over x or x over sine x both have a limit of 1. The cosine one works in either order in the sense of a different order of subtraction, and you'd still get the same answer. But this one does not work in the reciprocated sense because the reciprocal of 0 is undefined. So just to show you different variations that you might see, on the sine x you can reciprocate, on the cosine x you can switch the order of subtraction. Okay? And this one's not trig at all, but this could also be written as, how else could you write this expression? Right? The xth root of 1 plus x. Okay? And we will take a peek at that function in a minute, but let's think about if analytically we can make any guesses. So plugging in 0 gives us 1 to an undefined power. So there's obviously an issue there. It's not quite feeling like the indeterminate case because it's not 0 over 0, but definitely an issue. 1 raised to an undefined power. Think about plugging in something really, 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 really close to 0, like 1/1,000,000th. What is 1 plus 1/1,000,000th, essentially? 1. To, what's 1 over 1/1,000,000th? 1,000,000. 1 over 1/1,000,000th is a million. Yes? So this is going to be, it's not ever going to be exactly 1, but it's something very, very infinitely close to 1 being multiplied to the millionth power, so by itself 1,000,000 times. So what would you guess the limit would be? I think I would guess 1 as well. I mean, I wouldn't have any other reason. I'm not sure that that's correct because it's kind of a weak argument because it's not technically 1, but it's getting obviously closer and closer to 1. 1 over... See, the catch-22 here is that even though when you get this closer and closer to 1, you're also multiplying it by itself an extra number of times. So I don't know how those are weighing against each other. So this is just another rule. I'm kind of led to believe it's not going to be 1 just because why would it be a second rule? But if you graph it... Oh, did I type that in right? 1 plus x to the 1 over x power. The limit as x approaches 0. What would you say it is approximately? It's definitely between 2 and 3. What's special numbers between 2 and 3? E. I think it's probably like 2.7-ish. Second trace value 0.000001. 2.718. It's E, which is a complex something's happening that we really can't wrap our head around. So it's a rule that you just have to memorize. I'll be honest with you. That doesn't come up hardly ever. Because if it came up a lot, I would know it like the back of my hand. And I almost didn't remember what it was. So don't get caught off guard by it. It came up in this textbook. I don't think it came up in the old version of this calculus book, which is why I feel like it wasn't very familiar to me, and I kind of explored it alongside you. So don't get bent out of shape about it. It would be one that, you know, you'd have probably the calculator for. I don't know the mechanics that are behind it. Because, and again, the reason that I lacked confidence even in our guesstimate of 1, which was obviously wrong, is because while this is getting infinitely close to 1, every time it gets closer and closer to 1, you're just raising it to a bigger and bigger power. So how are those two factors working against each other and kind of weighing in against each other? You follow the dilemma there? Sometimes it's nice because, well, you know, it's getting smaller, then something else is getting even smaller, and so it's easy to say, okay, it's, you know, negative infinity, whatever. But this one, they're kind of working against each other. The base is getting smaller, but as a result, the exponent is getting bigger, and they're weighing against each other in a way that, without a calculator, we can't really quantify and figure out in our head. Does that make sense? So we obviously can use a calculator and just look at it and see that. And I'm sure, of course, there's some analytical algebraic proof out there that Einstein probably figured out that, you know, would be an entire college course exploring just that limit. We don't need to explore it. Some things we just take and say, thank you, Einstein. We're going to use that shortcut. I know. I like to understand things too, but there's some things you just have to let go. And just kind of take what these shortcuts that people figured out. All right, so how do we use these? First example, limit as x approaches 0. And we have a 3 times 1 minus cosine x over x. And so obviously this should be, you know, looking relevant. And also what you're going to see a lot is a mixture of those properties that we talked about, because this can be technically considered 3 times 1 minus cosine x over x. It can be two different functions where the rule is if you're finding the limit of two functions that are being multiplied by each other, so I'm really going to stretch this out and show more work than is really necessary, but you can think of this as 3 times 1 minus cosine x over x, as if it's two different functions, an f of x function and a g of x function. And the rule says that we can find the limits of each of those separately. And just multiply them together. So the limit of 3 is 3. And the limit as x approaches 0 of this 1 minus cosine x over x is 0. And 3 times 0 is 0. Okay, in the second exercise, you try to plug in 0, you're going to get 0 over 0. We manipulate. So manipulating in this trig sense is going to feel a little bit like identities did. You just kind of play around with it, hope some things will cancel. And obviously, if you change the tangent into a sine over cosine, you get a cosine to cancel. And then we're just looking at the limit as theta approaches 0 for sine theta over theta, which is one of our properties. That's just one. Okay? On the next exercise, given that we did that homework problem the other day, Jalen obviously already knows that this answer is 5. One of the strategies, though, and you'll see me use it again down here because this one's a little bit different, right, but still has this wrinkle of coefficients in there. One of the strategies you'll see is in order to use this property here verbatim, you have to be taking the sine, whatever you're taking the sine of, has to be the same thing that this is over on the denominator. So in order for us to use that property from above, the denominator would need to be a 5x. It would need to be sine of 5x over 5x. So make it that. And you can't just like make it a 5x because you're changing the function, but you can always multiply by 5 over 5. You can always multiply by 1 and change the appearance without changing the value. So I'm looking for the limit as x approaches 0 of this, and this part of it is just 1, sine of 5x over 5x. So then it just ends up being the limit of 5, which is 5. Adam. Right, because you can't square the numerator and the denominator. Correct. Yeah. There's no quick fix for that, because if it was the sine of x squared, you would need an x squared on the bottom, and if all you had was an x, well, I like that. You could just you couldn't square both, but you could multiply both by x. So let's do that. Sine of x squared over x. So we can't use our property right now, but you can always multiply by 1 in a creative fashion, which if I need this to be an x squared, I need to multiply it by an x. So I'll multiply by x over x. And so that'll make it the limit as x approaches 0 of x times sine x squared over x squared. So this will just be 1. And then I'm just looking for the limit as x approaches 0 of x, which is what? 0. X is so this would now allow me to plug in 0 for x, and your answer would just be 0. Does that make sense, Adam? Love it. I love your hypotheticals. That's a little bit different, because if you have an x squared here, you can't just make this an x squared. But what you can do here is you can split this up into sine of x over x times x, so that this portion can be your 1. You follow? But then the limit as x approaches 0 on this one, now when you reevaluate, you get 1 over 0, so that answer is actually undefined. Follow? All good questions. All right, on the next one, if I plug in pi over 4, and that's the limit I'm looking for the record, all bets are off. I can't use these at all, because I'm not approaching 0. These rules only work if you're looking for the limit as x approaches 0. So I can't use those here at all. I can still manipulate this, though, as if it's an identity. First, though, if I plug in pi over 4, what happens? If I plug in pi over 4, I do get 0 over 0. It's root 2 over 2 minus root 2 over 2. But nonetheless, it is 0 on the denominator and it's 0 on the top. So it is the indeterminate case. So, you know, again, it's easy to get out of the habit of checking for that, but still, check for direct evaluation doesn't work. We have the indeterminate case. So what can we do to manipulate this? We can change our tangent to sine over cosine. Then what could we do to simplify this? Clear the fractions, right? So maybe clear it by multiplying by cosine x over cosine x. And you kind of are going blindly into this, just hoping with your fingers crossed that something's going to work. If it doesn't, we'll have to go back to square one and brainstorm. But you distribute your cosine to get rid of your complex fraction. I'm not going to distribute the cosine in the denominator, and perhaps some of you can already see why. Why didn't I? What can I now do? Cancel, sort of. Cosine x minus sine x, and sine x minus cosine x will be -1. So this all boils down to just -1 over the cosine of x. So things did simplify down. Now I can directly evaluate, and I get -1 over the cosine of pi over 4, which is root 2 over 2. And then that just is going to reciprocate this. So I get -2 over root 2. And then when you rationalize, will be -2 root 2 over 2, and your 2's cancel, so it ends up being -root 2. So are you feeling the identity thing? Just manipulating trig functions. And then these pop up on your homework, so your homework's not all exclusively trig, but this should feel like what we did yesterday. E functions are tough in general. Lots of times they are calculator type questions, but sometimes they're factorable. Like this numerator, again, like we saw yesterday, difference of perfect squares. So that's e to the x plus 1 and e to the x minus 1. And then we get the e to the x minus 1 to cancel, and we can redirectly evaluate and plug in a 0. E to the 0 power is 1. 1 plus 1 is 2. So we get 8. So this last example here on the front is kind of tricky because almost reminds me, Adam, of your x squared question, the final one that you asked. You can't change what's in here. You cannot change that. You can't add on to that. You can't change that. So what we want essentially is sine of 2x over a 2x, right? If we want a 2x in the denominator, put one there. But you have to also put one in the numerator because you have to be technically multiplying by 1 so as to not change the value. But we are changing the appearance. So that'll cover that, so that will have a limit of just 1, so we can kind of cross that out. And in the denominator we have sine of 3x, so what do we want in the numerator? 3x, which again, you can't just put it in the numerator without also quote-unquote putting it in the denominator, technically multiplying by 1. So the sine of 3x and the 3x will have a limit of 1 as x approaches 0. So all we're left with here is 2x over 3x, which can be simplified because your x's cancel. And it's just the limit of 2/3. And so the answer is just 2/3. You can. It is because of those mechanics, it will work every time. I don't make it a rule because I don't think it comes up enough to justify that, but and it's really not defined in any textbook as like a rule shortcut, so I just don't do it, but I mean it will happen that way every time. Adam, question? Yeah. Yeah, you're correct. But I just kind of follow what are typical theorems that are used in math, and I don't. You can always over-create theorems and rules, right? And I would if I were doing 1,000 of them in a row. But if it doesn't come up that often, it's probably not worth it. Yes. So you tried using a double angle. Okay, so he tried replacing this with a double angle formula. So he immediately changed it to, let's play around with this, 2 sine x cosine x. all over the sine of 3x. I could give my numerator a 3x, which means I also have to give my denominator a 3x, so this will be 1. And then I do have a sine of x over x, so that will be gone. You see that? Because the limit of that is also 1. So then I'm just left with the limit as x approaches 0 of 2 cosine x. And I get over 3. And it does work. Because now if I evaluate and plug into 0, cosine of 0 is 1. 2 times 1 is 2. 2 over 3 is 2/3. So it does work. Okay. But that's how identities were, right? Totally different methods could still, you're doing appropriate substitution. So it sometimes it doesn't in a way that's easy enough to see. It should always still work out, but the math behind some of those might lead you down a path that's like really confusing. This is more confusing, but still totally, you can still follow it and see that it's 2/3. Good. Glad you said that. Okay. Last two on the back. So this one is sine of x over a cubed root. I don't like cubed roots. I don't know about you guys, but my instinct is to make that a 1/3. Do you guys have the same instinct or no? I just don't know if it's because I have been doing math for so long or if that's just normal people behavior. But you do that too, Stephen? So, what do we want the denominator? What do we wish the denominator was? X. What could we multiply by to make it x? Correct. Capitalizing on exponent rules. If I multiply by x to the 2/3 over x to the 2/3, this denominator does become x to the 3/3, or just x. So now it's x to the 2/3 times sine of x up top all over x. And your sine of x over x cancels, or it doesn't, I shouldn't be saying cancel. I should be saying that the limit of that portion as x approaches 0 is 1. And then we can evaluate 0 to the 2/3 power is 0. Okay, and then one more E type of function. If I do plug in the natural log of 2, I do get 0 over 0. So, perfect cubes, yes. Okay, so that numerator factors into e to the x minus 2 as the binomial if I'm doing difference of perfect cubes. This is e to the 2x. The middle term is plus 2e to the x, and our last term is 4. On the denominator, we have the difference of perfect squares, e to the x minus 2, e to the x plus 2. And then we lose our factor. So I think now we can directly evaluate. I'm going to have to be careful with this. So when I plug in the natural log of 2 up top, I get e to the 2 times the natural log of 2 plus 2e to the natural log of 2 plus 4 over e to the natural log of 2 plus 2. On this middle term, the e and the ln can cancel. Agreed? So this is just going to be 2 times 2, which is 4. Are you with me there? And the same thing on the denominator. This e to the ln of 2, the e and the ln will cancel so that this will just be 2. What's this situation? We can't cross those e and that ln out because we have this thing in the middle. What do we do with a coefficient of a log to get it out of there? Bring it up as an exponent, correct. So once you're there, now your e and your ln can cancel, and that will just be 2 squared, which is 4. So this ends up being 4 plus 4 plus 4 up top, and 2 plus 2 on the bottom. So 12 over 4 is 3. Okay? So I don't think it's a difficult day. It's just a couple new rules to get used to. Kind of manipulating with a couple new tools